Well, this is supposedly the title of my presentation, The Next Generation of Astronomy Experts. When they invited me to come here, they suggested this title, but I really didn't have any idea what it was all about. So it took me a while to start giving myself an idea of what it was about. So this is the official title, but the real title, I will say, is like this: Bringing Science to the General Public, High School and University Students Using Gaia. Okay? Uh, Let me start by saying that communicating science to the general public and students is a very, very important task. It should never be dismissed. And I have this engraving from the famous Michael Faraday lecture he used to give on Fridays on the Royal Society. Okay, it was always very important to make contact with the public. Now, astronomy is very appealing to the general public. I can guarantee that if you choose any city on the earth with more than, let's say, 50,000 inhabitants, surely you're going to find that there's a group of amateur astronomers. You are not going to find a group of cryogenic physics amateurs or solid state physics amateurs. You are going to find a group of astronomy amateurs. So that tells you something. Astronomy is very luring for the general public. So, since this is the case, it can be used to approach the general public if we are doing outreach or to students for education. Okay. Now, the point is that in many cases, the general public really doesn't have very good idea of what an astronomer really does. And in fact, I find amusing that in many of the cartoons that they have of observatories, the telescope is sticking out of the dome. That's a general misconception. Okay. Well, as I say, as professional astronomers, we have a great responsibility in bringing science to everybody. Okay. But my point is that it is not only information and images that we should deliver. We should use astronomy as a tool to convey the culture of logic reasoning and healthy skepticism. That's the real important message. Okay. We transmit information, we tell them about a particular thing, but what we should try to do is to make the general public, the students, to be scientists, to start thinking about the reality around them as scientists, to be skeptical, to have logical reasoning. If we are able to do that, regardless of what they do in life later on, we will have achieved something really important for our society. The problem is how to do it. Okay, first a disclaimer. I'm a professional astronomer, but I never had a formal education on pedagogy. Okay, so what I'm going to tell you about is just a product of many, many years. So don't ask me how many, of teaching and giving outreach lectures. I wish I had had early in my career some contact, some formal information about people who really know how to communicate these ideas. I have to learn it the hard way through the years. So what I'll present is based on empirical experience only. Okay? And here are some important points I want to give you. The first is that since we are the experts, supposedly, we are the ones that have to reach out to the audience. Okay? And we should design our talks or lectures starting from the intended audience mindset. And this is very, very important. I've seen this error being made all the time. We start from our ideas, and then we'll say, how are we going to adopt them so that people can understand me? That's the wrong way to go about that. You have to start putting yourself in the shoes of the general public, of your audience. And from that, start building a bridge to where you want to get. That's very important. Okay. Images and even more animations are very powerful tools. Analogies are also very powerful tools. They are excellent to bridge the gap between the audience and the concept, the facts of the abstract ideas that we want to communicate. So analogies are very important. And the most important part of a talk or a lecture is the very beginning, because that's when you are going to really grab the attention of the audience. If you start very badly, then you're never going to recover the attention of your audience. So the very first part should be very attention grabbing. I'm going to give you hopefully 3 examples if I have enough time. One is at the general public level, another is for high school students, and the last one it will be at the college or even graduate level. So let's start with the general public level. And this is an example of analogies. Okay. And here I'm going to quote Maxwell, who said, "For the sake of persons of different types of mind, scientific truth should be presented in different forms and should be regarded as equally scientific, whether it appears in the robust form of and vivid coloring of a physical illustration or in the tenuity and paleness of a symbolic expression." So here's a very famous physicist telling us that it's very important to be able to convey the same message in different ways. What do you do? This is a question that I get all the time. I'm sure many of you also get it, even from some of my relatives. I've known them for so many years, and they say, "Well, what exactly is that you do?" So here's a possible answer. I work in galactic dynamics. I use the positions and velocity of stars to trace the gravitational forces acting on them. And from this, we can infer the potential of the galaxy, and from this, the mass distribution. Well, there's a lot of things to understand here. What exactly is galactic dynamics? How can you get the gravitational forces from the positions and motion? What the hell is a potential? How do you go from a potential to a mass distribution? There's a lot of things here. Okay. You're playing with the concept of acceleration and mass, Newton's laws of motion, universal law of gravitation, the concept of slope in order to go from the potential to the force. Okay. This is a lot to ask. So you have to be careful. So here's where an analogy can work. So when they asked me that, I said, look at this tree. Okay, this animation, I hope it works. Oh, yes. There's a tree. And I can see that it's moving. Why is moving? Oh, because of the wind. The wind? What is that? I don't see the wind. I only see the tree moving. Oh, come on, the wind. The air is moving. And that's pushing the leaves of the tree. Ah, so you accept that there can be something which is invisible and nevertheless having a physical effect of something that you can see. Of course, everybody knows about the wind. Okay, if we accept that, we can say that by looking at the tree, we can guess the direction of the wind. And furthermore, if we are a bit more careful and start measuring the bending of the branches, we can even estimate the speed of the wind. Well, that's what I do. I watch trees. But in this case, the tree is the galaxy, the leaves are the stars, and the wind is the gravitational force. That's what I do as a professional job. I watch trees. Okay? So you see, I'm using an analogy that everybody understands in order to explain what I'm doing. And the analogy goes here from trees to the galaxy, leaves to the stars, wind to the force of gravity, and I'm introducing the concept of direction and magnitude. Okay? So I'm making the public accept that invisible things exist. Invisible things can have an effect on visible objects. I'm introducing the concept of a vector, something that has direction and magnitude. And this is a very familiar analogy that everybody understands. So I'm achieving a lot by using this. So this is an example of a good analogy, I think. Now I'm going to describe a particular exercise at the high school level. And this is the idea that Judith was telling us yesterday. It's just that I work a little bit, some aspects of this marvelous exercise that Judith presented us yesterday. What is the problem? Well, you have a rotation curve, and from that you can produce an image like this that was produced by Bob Benjamin from the University of Wisconsin a few years back, in which you see the center of the galaxy, the sun, and then the contours of equal heliocentric radial velocity. So from the rotation curve, you go to these contours. Okay? So the basic idea, the theoretical part of this project is that you get from the rotation curve through this very simple equation. There's no calculus involved, it's just trigonometry. And then you can create these figures. In the upper part, you have what you get with a flat rotation curve, and the lower part with the Keplerian rotation curve. Okay, how do we go about this? Well, there are very many problems that we have to confront. What is a rotation curve? What is a radial velocity? What is a heliocentric radial velocity? When is positive and when is negative? Because in this diagram, the red contours are negative, are receding objects, and the blue curves are approaching objects. And then what are isocontours? I mean, to understand a diagram with isocontours is not easy. How do we get from the rotation curve to these contours? And what do we learn from this? So there are lots of things that we have to address here. Let me start with rotation curves. And in many cases, we start drawing rotation curves without realizing that to a lot of students, they don't understand what is the difference between an angular and tangential velocity. That's something that we have to address. And then we can tackle the question of what is a rotation curve. And then we can show different types of rotation curve, rigid body, flat, Keplerian, and finally the concept of differential rotation. And we can achieve this with very simple examples. For instance, here the relation between tangential velocity and angular velocity. But I tell them that the first one is length versus time, and the second is angle versus time. But I can animate that, and I can show them when two objects move with the same angular velocity, and contrast them when two objects move with the same tangential velocity. So you start visualizing what is happening here. And once they understand that, I can show them what happens when you have a flat rotation curve, when you have it was a rigid body rotation, and now it's a flat rotation curve. And we start seeing the effect of the differential rotation. And finally, we have a Keplerian rotation curve that produces a much faster winding problem, okay? And then at the last part of the exercise, I animate the three of them so they can contrast. By looking at this, they really get to understand what is the physical meaning of the rotation curve, rather than just showing them a plot. Okay? Then I have to put them in context. We have to describe the galactic layout. So we introduce this system of coordinates, x, y, and the polar coordinates we're going to use, r, theta, where is the galactic center, where is the sun. And then we can show them a star going around, and we introduce the concept of line of sight, and that the line of sight is not fixed, it's moving with the star. Then we can introduce the radial and tangential axis and animate all of them, okay? And now they are going to see how the star is going about, okay? And how the velocity vector is changing with respect to my axis, my radial and tangential axis, because they are given by the line of sight. Then, from that, I show them the radial and tangential components, and then I talk about the Doppler effect and the radial velocity, and astrometry, and how that we go the proper motions, and then the tangential velocity. We can all of that, we can show that then the velocity vector, as it rotates around in this system, is going to generate different magnitudes of these components, the radial and tangential components. And now I put it in the galactic context, and I'm showing only the radial heliocentric velocity, and they can notice that in this line directly towards the galactic center, the velocity is going to be null, and it's going to be maximum on this tangential line and minimum on this other tangential. But by animating this, they can visualize what is happening, and then it's easier for me to plot a curve. This curve will be very abstract, very difficult to understand. But now that they have all of this, and I can point many points here along the circular orbit, they can understand what is happening here. For instance, in points A and D, the velocity is null, and that's exactly what is happening. Okay? But once we have that for a given circular orbit, we can use many circular orbits. And we can make a plot for each of those circular orbits. And once we have done this, what is the natural step to follow? Well, stack all of them and produce a two-dimensional surface, in which now you can see for every location of the galactic disk what is the predicted heliocentric radial velocity. Now we have to understand isocontours. So we have to make a step aside in order to talk a little bit about this. The challenges here are, well, the concept of isocontours of a 2D function, and to learn to read an isocontour map as a representation of a 3D surface. So we start with a very simple curve that is easy to understand. And then we introduce a fixed height plane, and then we move it around and we plot the intersection in red, and we tell them, well, those are the intersections. Once you have that, you can draw those isocontours as the floor of the 3D figure that you're producing there, all by itself. But with this animation, they can understand very well what the isocontours are. And now we can put everything together, and we go back to our stack curves that we have for the flat rotation curve. And I can show them the isocontours. Here's the galactic center, here's the sun, or here's just the isocontours. But because of all the previous work that we have done, now they can understand this very well without problem. But we had a very gentle approach step by step. And then we can do the same for, let's say, a Keplerian rotation curve, and they can see what are the differences in these contours. And then we can take the difference of one versus the other, the flat rotation curve minus the Keplerian rotation curve, and that is going to tell us right away where it is that we should look in the galaxy, that we're going to find the maximal difference between these two hypotheses. So they can start aiming for where to look in the galactic disk for this difference. Here's the map of isocontours of differences. Okay. Of course, there's some math involving this. I will skip all the mathematics, but they are very simple. They're at the high school level. There's just trigonometry. I only need for them to know the sine and the cosine laws. That's all what I need. No calculus required. But I don't have time to get into this. I have slides, I have animation, I can show you all of that, but I don't have time. Now, let me give you a few highlights about the college graduate level. I've taught a course on galactic dynamics for 30 years now, and something that I have never liked in astronomy is that most of the people, most of my colleagues, don't have a physical intuition about gravity. Gravity can be very counterintuitive in some cases. And since gravity is behind everything in the universe, we should have, regardless of what we do, what is our field of interest, we should have a little bit of a sixth sense about gravity, how it works. And that you rarely find that. And I think that the people who teach galactic dynamics are the ones to blame, because we tend to be very analytical, full of math, and you have to dig through half of the book before you start finding interesting astronomical applications. And I think that's the wrong way to go about that. I think that in mathematics, you have the analytical part, but you also have the geometrical part, and they are equivalent. And when we teach something like this, galactic dynamics, we should be talking to both sides of the brain. In fact, I've been working on a book that I call the Galactic Dynamics for the Other Side of the Brain, and I'm finishing. I'm going to publish it in the internet, I think, in the autumn, and it's full of illustrations because I don't relinquish the formal part, but I'm illustrating with lots of mathematically correct figures, and that can help you to understand what is happening. Let me show you some examples. Here I'm quoting Einstein, who said, if you can explain it simply, you don't understand it well enough. Well, here's a topic that you see in many instances in astronomy, with binaries or with galactic rotation or with accretion disk. You have the equation of motion, and since you are in a rotating frame, you have to include the centrifugal term and the Coriolis term. And this is a page taken from this book, Galactic Dynamics by Vinnie Tremaine. It's the standard text in Galactic Dynamics. And this is all what they show you. And then there's this figure of isocontours. And from that, the student have to understand everything here. Well, here's the same figure, but in 3D. Now it's much easier to visualize. And you can see the Lagrangian points, and you can see the minima and the maxima. And not only that, you can do animations. Here I'm putting several frames in which the flat plane, the green plane, is a constant Jacobi energy surface. And then you can see, as you lower the value of the Jacobi energy, the allowed regions to the orbit are shown in green, and you see that you start squeezing those regions until they disappear at the center. And by the way, you can understand why is that when a satellite system is being destroyed by the galactic tidal field, you have two tails, a trailing and a leading one, because you are losing particles through these opposing saddle point Lagrangian points. You can see it directly. Here's another example. We use a lot something that was devised by Henry Poincaré called the Poincaré sections. And these are some sections that you take in phase space and you plot the intersections of the orbit, and that tells you a lot of information about the orbit. Well, I took these figures from the book of Vinnie and Tremaine, and that's all what you get. But what if you use a figure to illustrate what is happening? Okay, we have a four-dimensional phase space, and this green ellipsoid is the volume of constant energy. And here comes Poincaré with his knife and takes a section, and then you see the orbit coming out and in, and you start plotting all the intersections. That is helping a lot to understand this figure. But this is just systematically. This is not mathematically correct. Let me show you something that is mathematically correct. I did this with a program called Mathematica, and this is for the logarithmic bar, potential bar. Okay, so this is exact. And I'm showing you the x coordinate with its velocity, and then this is the y coordinate. And this almond shape that you see here is the constant energy volume. Here's this section, and then you can see the orbit going around and around in a torus. And the shadow on the xy plane is what you see in real space. Now you can understand these loop orbits because of what is happening in phase space. And I'm not cheating. This is mathematically correct. But then we can move the initial conditions without changing the energy. And you can see, oh, yes, you can see how is that we go from loop orbits to box orbits. When you just look at the real space, it's very hard to understand how you go from loop orbits to box orbits. But when you have this continuity in phase space and looking at the intersections, you can clearly see what is happening. So images help a lot, even at the graduate level. Okay. The last example is the Schwarzschild method for building galaxy models. It's a complicated things to describe. This is the page from the Vinnie Tremaine. But here's my explanation. You start with a mass distribution, whatever you want, and you solve Poisson's equation, perhaps numerically, and so you have the density and you have the potential. What do you do next? Well, you introduce a mesh, whatever mesh you want. The geometry doesn't matter. I'm putting a Cartesian mesh because it's easier to visualize. And once you have that, you compute the fraction of the mass of the model in each cell. And so you can plot this histogram. I'm cheating a little bit because the base should be three-dimensional, not two-dimensional as I put it here. So let me that pass. Once I have that, what do? Since I have the potential, I can compute a lot of orbits. So I have a library of orbits, okay? And I can convert each of those orbits into a histogram of occupation. What is the fraction of time that a given star in that orbit is spending in each one of the cells? So I have a histogram for each orbit. So what I have to do is find the linear combination of this histogram that reproduces the overall system. Once I've accomplished that, I have self-consistency. I got a dynamical model. I think it's a lot easier to understand this way than in the standard way. Okay. Some final words. Our understanding of the universe is by means of mathematics. But math has two sides, analytical and geometric. Mathematically correct figures can be a powerful tool. We can use a more geometric approach without losing rigor. When engaging audiences, outreach or teaching, we should aim to communicate to both sides of the brain. Well-devised analogies are another powerful tool, especially for outreach. Remember my example of the tree. We should use the new media technologies, but in a manner that engages people and makes them think. We shouldn't present to them everything already digested. We should make them think. When they discover something by themselves, it's a lot more attractive. Special effects and such gizmos are means, not ends. We should use them, but not too much. I mean, at the very end, what is important is the message to make people think. And the tools are these animations and all of these sound effects, but they are not the end. And we must swim against a torrent of misinformation. Unfortunately, on these days, there's a lot of misinformation on the network, and we should learn to swim. We should start really making use of all of these social network tools in order to transmit the correct message. Thank you.
Thanks a lot, Luis. First of all, congratulations on this magistral class of professors like you. I only want to go back up to the past, to be a student like Judy, to have the lucky of to have professors like you to show so intuitive, so illustrated the things that are so theoretical that when I study, it's only books in black and white and for formulas, etc. So this is nowadays in 21st century we are lucky to have all this material and tools and have professors like you that show us to and learn to the new young students like this.
So, thanks for your work, Josefina. But I think that, okay, we have these modern tools and they are very powerful, workful, and we can use them. But I think that in many cases, we scientists, we have had the wrong idea of the wrong approach towards the general audience, because you can communicate science from the past. You have the tradition of the Michael Faraday lectures, for instance, talking to the general public, well, the British general public. But I mean, there have been, in the history of science, there have been people who have always been very attentive towards the problem of communicating science to the general public.
Nowadays, there are more and more involved to show the general public their investigation and so on.
Well, let me tell you, I've enjoyed a lot this conference, and it has been an eye-opener to me, because I know several efforts in order to bring science to the general public in my country. Well, now that I'm here, I see so many descriptions of so many projects, very interesting, with different approaches, that I think we should have more and more conferences whose aim is only how to communicate science to the public. And so we can teach from, we can learn from each other, and we can organize some wide-ranging projects.
create these analogies? Do you have a kind of method to develop these analogies, or just thinking and thinking? And the second question is, once your book is available, how we can get it?
Okay. About the analogies, I follow a very strict methodology in the form of a good bottle of wine. And once I have finished the bottle of wine, I come with a good analogy. No, I mean, I think about a problem and I keep bouncing in my brain, and all of a sudden the idea flashes in front of me, and I start working on that. There's no method for that. Okay. And about the book, well, I'm going to release it I have my homepage in my institution, and I'm going to release it in the autumn sometime. If you want a copy, just write to me. I have my email address there in the lower corner of the slide.
Other one, yeah.
Only in what?
Spanish.
Spanish. No, it's not in Spanish. It's in English. Yeah. And it's not a formal book in the sense that it's going to be printed and so. No. This is, I just put it in my homepage, and whoever wants to download it is welcome to do it. Yes, but in this case we're talking. A very specialized audience, because this is a graduate level course on galactic dynamics, and nowadays most of the graduate students know at least how to read English.
Okay, I think that we thank Luis again for the great talk.
Thank you.
The great analogies. And now we move to the